Hello everyone. Today we are going to be discussing ETAP iDLS and its application in city distribution network. The ETAP iDLS is an integrated model-driven controller-based system. It utilizes real-time operational digital twin to validate, optimize, predict, and manage load shedding or curtailment. Today, we will be demonstrating ETAP iDLS capabilities, the direction where power system utility are heading, the requirement for a low-shed system for distributed network, how ETAP iDLS is addressing the industry requirements, additional features of iDLS that bring iDLS ahead of any load shedding solution in distribution networks, and we will end with a case study. The ETAP iDLS controller system uses a novel technique using digital twin models to perform load curtailment. It determines the minimum required load to shed based on the digital twin model, system topology, and real-time operational data. It then selects the optimal combination of load to shed based on type of trigger condition, load group priority, time of day, and more. It has integrated options to minimize the impact on quality of supply, improving reliability indices. The digital twin model and load shed calculations account for distributed energy resources, DER. The ETAP iDLS is a critical component of the distributed energy resource management. iDLS is designed for geographically dispersed systems such as transmission, distribution, and industrial dispersed systems such as oil and gas production fields. The transformation that is occurring in the infrastructure and operation of electrical industry is major. Most power utilities are moving away from fossil fuel generation to renewable systems. In addition, decentralization is occurring where resources are now smaller distributed generation. They can be fossil fuel or renewable. This is happening at the transmission and distribution side. Independent system operators, ISOs, regional transmission operators, RTOs, and distribution companies must coordinate more than ever as generation conditions continuously change. As distribution companies perform load sharing at feeder levels, they will not only be dropping loads but generation as well. DERM systems must adjust to significant changes and demand in operation is changing. Distribution load sharing system must be able to determine load sharing requirements and operating conditions. For this, visibility and understanding of a system is a must. Minimize impact on quality of service. As loads and feeders are being dropped, customer satisfaction drops. The system must be smart to minimize the impact. Account for distributed energy resources DER. Determining loads to drop must account for DERs as it will influence voltage support. Coordinate limits with ISOs and RTOs. Demand transaction limits between ISO and RTOs must be accounted for to make sure that unexpected demand in distributions do not affect the transmission side. Distribution networks are very dispersed. The load shed system must utilize available communication technology with intelligent technology to centrally manage the load shed for entire system and at the same time have a fast coordinated response. To calculate the required load shed under different conditions, such as overloads, under frequency, under voltage, the solution must be very intelligent. Distribution networks, although most of the time are operated radially, can change topology during reconfigurations during maintenance procedures. Changes in the topology can happen as sub-transmission systems. The load shed system must have the visibility of the entire network. Topology changes might cause loads to switch feeders, create unbalance and/or overloads even at the sub-transmission side. With DER in the mix, power reserves must also be calculated to minimize impact in the system. Network component capacity must be monitored as well. With the rapid changes in the networks, demand increase to the drop of DER generation can be overlooked and devices can be overloaded. Real-time operation visibility is a must to understand how much to drop and where to drop it. The location of the disturbance as well as its type must be known as well to make intelligent decisions. The iDLS controller builds real-time and analytical digital twins from the ETAP model. The load sharing controller takes advantage of the electrical model information to understand the capacity of each component, connectivity, and topology. In addition, the disturbances are also identified in such topology. With location of the disturbance, component capacity, topology, and real-time data, the iDLS system calculates how much and where it needs to shut the load. This is all done before the actual events happen, proactively preparing substation controllers or RTUs and itself to respond in case the disturbance happens. In short, the iDLS controller generates digital twins of the complete distribution network. It has an integrated topology processor using real-time data to understand changes in power flows. Initial load priorities are defined during configuration and can be optimized in operation. The twin model provides the components' capabilities. It communicates to DERs to understand available generation. Special algorithms are defined to understand the interconnection capacity with transmission. All this information is used to calculate how much to shed and then optimizing what loads to shed, avoiding overload shedding and therefore losing revenues and customer satisfaction.
As you can see in this video, ETAP brings in and displays the real-time data from the field for all telemeter devices in the same model that is used for simulation. This combines the power of the electrical intelligence of the distribution system model with the real-time awareness of field data. The field data along with any state estimation result is displayed on the one-line view in ETAP in an easy-to-read, analyze, and operate manner. The field measurements can be plotted for more in-depth analysis on the real-time plot viewers or can be displayed in an operator-friendly HMI. The operators can monitor the health of the distribution network from such a view and take actions accordingly to maintain the reliability of service to the customers. The real-time system is constantly monitoring the operating conditions throughout the system, such as loading levels, frequencies, currents, voltages, power factors, and is aware of the current topology of the network along with any temporary interconnections such as jumper or a cut. All these electrical signals measured from the field along with any non-electrical real-time data such as key energy market parameters, weather data, set points requests or recommendations from the RTO or ISO, as well as any maintenance, repair, or breakdown activities being performed on site, are brought into the ETAP real-time system and used by the distribution load sharing engine for making intelligent decisions. The load sharing data is monitored from an easy-to-use and operate load sharing monitor application, which displays the list of triggers and loads that will be shed if any of the conditions were to become true. The what-if analysis is done continuously by the ETAP Intelligent Distribution Load Sharing Engine, and the results are displayed on the monitor as well as armed to all the controllers on the field. The monitor displays the amount of load that is selected to be shed for every scenario, as well as a list of loads to be shed based on the user-defined priorities. Non-essential loads with the lower priority will be selected to be shed first based on the system conditions and operating levels. Essential loads will be selected only if the non-essential loads cannot satisfy the requirements. There may be some loads such as hospital, clinics, emergency services that need uninterrupted reliable power supply, and the load shedding system will not shut them and ensure that the system reliability is maintained to provide services to these key loads. The iDLS system monitors its own health and the health of any field devices used in the load sharing process. The communication status, the status of each trigger at every node point, is monitored continuously. Load sharing events are also recorded and displayed to the users to piece together the sequence of events, as well as analyze the accuracy and effectiveness of the load sharing action in real time. These events display the timestamp, the trigger that was fired, the calculated amount of load to be shed, as well as the amount of load that was shed. Any breakers or switches that may have failed to operate due to any reasons will also be displayed in this window.
Many utilities define and track quality of service in different ways. In most, the track reliability indices derive from the number of interruptions and duration of interruptions. The load sharing system must be able to minimize the number of customers interrupted, minimum amount of load to shed, and minimize the number of interruptions of each customer. The quality of service can also be based on the quality of supply. especially in industrial areas where voltage distortion and low voltage conditions can cause interruption of the internal processes. In this case, the load shed system must understand the voltage support that DERs can supply when performing load shedding. Both of the above lead to better customer service. Some utilities purely track quality of service based on customer inquiries. Optimizing reliability indices and quality of supply will minimize customer inquiries. Incorrect load sharing can lead to loss of revenue and unhappy customers. In regulated regions, it can also lead to violation penalties for low reliability. The ETAP iDLS solution provides tools and capabilities to minimize the impact on quality of service. Dynamic load shed priority is one of the tools. The iDLS allows you to classify customers and feeders such as critical, industrial, residential. Priority can then be adjusted based on the type of customer. The iDLS allows you to track total load connected and number of customers connected per feeder. This is important when deciding the priority of feeders in the case that a large number of loads need to be dropped. As load shed conditions happen, the iDLS tracks a number of trips that a particular load shed point, feeder or loads are dropped. It provides a dynamic priority algorithm that prevents a single customer or group of customers to be dropped all the time. Priorities are dynamically updated based on such an algorithm. This functionality saves hundreds of thousands to millions of dollars on penalties due to low reliability or poor quality of service. The Load Sharing Configuration Manager is used to define the load sharing philosophy for distribution systems. The manager allows the user to create a master list of all the loads that will be participating in the load sharing program. The user can define priority of each load based on their importance. For instance, street light loads can be shed first in case an emergency load shedding is required. Critical loads such as hospital, clinics, and other emergency services can be excluded from this list and thus will not be considered for load shedding. Information such as the number of customers connected to each feeder is displayed here and can be used to minimize the number of customers that experience power outage. The classification information such as the usage type of the feeder, that is industrial, urban, institutional, mixed usage, rural, or pump feeder type is displayed here. The administrative classification such as the division, substation, feeder, and any RMU information is also displayed here for each feeder. Additionally, user can create custom classification based on voltage levels, criticality of loads, or as is desired. The trigger information can be specified in the Triggers tab of the Load Sharing Configuration Manager. A trigger is any event that causes load shedding to occur. For example, underfrequency in the system, excessive demand in a system, or overloading of a transformer. As can be seen here, the user can define the type of trigger, such as a fast response trigger that gets fired as soon as the event is detected. For example, in case of loss of distributed generation or transmission line. Overload triggers monitor a sustained condition for a period of time and take action accordingly based on the user-defined delay time. For instance, overload of a distribution transformer or a feeder. Schedule triggers are one-shot triggers that are executed at the time of upload of a new load shedding schedule to the iDLS engine. These are used primarily for rolling blackouts, also referred to as rotational load shedding or feeder rotation. The user can customize the load sharing philosophy according to the specific requirements, scenarios, and behavior from the Logic tab. The logic can be easily customized using the wide variety of functions, measurements, and property. The user can compile the logic and test it in simulation mode before deploying to the actual production system. The user can create different schedules using the Schedules tab of the Load Sharing Configuration Manager. The schedules allows the user to customize the priority of loads based on the time of the day, week, season, or special occasions. For example, certain feeders are more heavily loaded during the day and lightly loaded during the night times. Certain types of feeders require uninterrupted power supply during specific times of the day and can be shared at other times. Certain industrial loads have contracts that specify allowable times for any power outage. Violations of these terms can cause the distribution company to face heavy penalties. Additionally, to ensure that all the loads are evenly distributed throughout the day, week, or month, the priority needs to be adjusted dynamically to allow all loads at the same priority level to experience equal amount of load sharing. Certain customers may face more outages than the customers, and this may lead to complaints and customer dissatisfaction. Thus, the ETAP iDLS system constantly monitors the number of outages faced by every load on the system and adjusts the load priority dynamically. This happens in real time and no user intervention is required. The utility can also enforce rules such as allow all loads to be shared a maximum of once per day or say twice a week. The rotation tab allows the user to define the list of schedules for different times of the day. The list of schedules for one 24-hour period is called a rotation. Different rotations can be created based on the day of the week, month, special occasions, or holidays and season. These can be combined together to create the load sharing calendar for an entire year. This is useful for automatically adjusting the priority of loads based on time of use, as well as to quickly create a rolling blackout schedule for a period of time. The communication parameters for the field equipment can be mapped using the Communication tab of the Load Sharing Configuration Manager. This allows the system administrator to effectively monitor the health of the load sharing system and ensure its effectiveness. As we discussed before, quality of service is important. The load share system must consider the impact on voltage support. Monitoring the DERs is important to calculate the available reserves. But in addition, the load share system must understand the response of the DERs for a determination of the available resources. As more and more DERs are added into the systems, the load shared system must be able to evaluate and validate the system response as load and generation grows. In addition, it must be able to measure the unbalance of generation or load when load shed happens. The load shed system must coordinate with the dispatch of DERs. The ETAP iDLS system is integrated into the DERM solution of ETAP ADMS. The Operation Real-Time Twin model includes DERs such as rooftop solar systems, energy storage systems, and any other DER. It communicates with the volt-var optimization systems and works with the feeder capacity calculations to determine strategy of load sharing. The ETAP iDLS solution integrates with the ETAP DERM solution. It monitors all distributed generation assets. This includes grid interconnection, fossil fuels, generation, renewable, and energy storage. The volt-var optimization system is in charge of performing voltage support to maintain the quality of service. It monitors as well as regulates all available voltage support components such as transformers, voltage regulators, capacitor, and inverter. Low voltage support objectives in the volt-var optimization study include conservation voltage reduction, minimization of power losses and optimization of a voltage profile. The ETAP iDLS system allows for detailed monitoring of your DERs including its microgrid controllers. Distribution companies must share the forecasted demand with the ISO or RTOs. ISOs and RTOs use this information for the generation unit commitment schedules. The implementation of a load shed system must include load forecasting so that the distribution utility can share the demand schedules. It must also be able to export demand to send to the ISOs and RTOs. The ISO or RTO returns its demand limits for the distribution company. The load shed system must be able to reach such limits to determine maximum capacity for the transmission grid. It should also have the capacity to enforce such schedules to prevent exceeding the capacity from the transmission grid. The interconnection with the transmission must be monitored and technical capacity protected by the load shed system. ETAP iDLS comes with continuous update of demand schedules. It is integrated with short-term and long-term load forecasting. Demand schedules can be generated 24 hours to 1 month ahead using the short-term load forecast and planned with the long-term forecast for years ahead. The Inter-Control Center Protocol (ICCP) communications built in the controller allows you to send and receive schedules automatically. The automatic import of transmission demand limit schedules are read automatically by the ETAP iDLS for reserve calculations and to enforce demand schedules. Protection on the interconnection is also built in, where ETAP iDLS monitors and acts as overload protection of transmission system interconnection, such as transformers and lines. As can be seen here, the ETAP iDLS system continuously compares the power scheduled to be drawn from the grid and the actual power demand at each of the transmission substations. Short-term load forecasting approach is used to forecast the power demand for the next few days at 15-minute intervals, and a 24-hour contract may be made between the distribution company and the grid operator specifying the maximum amount of power that can be drawn in each 15-minute interval. The power limits are also influenced by the system frequency. There can be multiple bands of frequencies that limit the amount of power that can be drawn and thus change the calculations for load shedding. For example, the load shedding demonstrated here considers 4 bands of frequencies, set points 1 to 4. The amount of power that can be drawn at each transmission substation changes with the operating frequency band, and it changes the penalties incurred by the distribution company on the amount of excessive power demand. The ETAP distribution load sharing system can intelligently monitor these parameters and make decisions to reduce penalties faced by the utility, as well as minimize the number of loads that get shed, thus effectively increasing the quality of the system. In this demonstration, the two transmission substations are not synchronized with each other, and thus the entire distribution network effectively operates in a split configuration. The ETAP iDLS system effectively tracks the two subsystems and monitors the conditions for them simultaneously. The ETAP iDLS system is capable of handling multiple such subsystems. In this case, there is a net overloading on the RC Green substation, which is in subsystem 2. Thus, loads from the subsystem 2 are selected to be shed, as well as to reduce power demand from that subsystem. In addition to this, the overloading of multiple transformers and feeders can be monitored and prevented using ETAP iDLS. The transformer overloading triggers monitors multiple power transformers and distribution transformers and compares the operating values against its ratings. The users can define the delay time to allow the system to monitor sustained overload for that duration. If the overload continues to sustain even after the time delay, then a command is sent to shed some of the loads directly connected to the transformer that is overloaded. The ETAP iDLS system is aware of the system topology and is thus able to shed the optimized number of loads to prevent the transformer breakdown. Similarly, the overloading conditions of feeders throughout the system can be monitored based on the operational set points, and decisions can be taken to prevent sustained overload on these as well. Lastly, the load shed system must be coordinated. Individual load shed per substation typically does not work as it does not consider the impact on the rest of the system. The load shed system must be centralized in configuration and decentralized in action as it needs to act on the entire system. It should consider the entire system topology and operating conditions. It must respond fast to underfrequency and undervoltage conditions. It should use entire system power flows to prevent overload conditions in the system. The ETAP iDLS system is optimized. The load shed controller monitors the entire system, performs the predictive load shed calculations, and loads the ETAP ICE RTUs. The ICE RTUs receive the triggering condition and perform a load shed. This is indicated from an event. Note that the RTUs must be able to continuously receive information from the ILS controller and must be capable of doing so. The ICE RTUs are designed to receive very much information in very short time. The iDLS controller can also work with third-party RTUs. In the case that the RTUs cannot receive the information continuously from the iDLS controller, the controller can hold the predictive load shed tables, receive the triggers, and send the control commands to the RTUs. Now, let's take a look at the additional features of iDLS that places it ahead of any distribution load sharing system in the market today. As with any other real-time application from ETAP, the load shed system can be designed and tested in ETAP, deployed to the load sharing controller, and updated during operation. During the design stage, the load shed logic engine communicates with the ETAP analysis package for validation of the response of the electrical network. During the deployment stage, the load shed controller can deploy its result to ETAP for validation and response of the electrical network. With other systems, you will normally perform the test with third-party real-time systems. In ETAP, it is all integrated and communication ready. During the operation stage, modifications and validations can be performed in ETAP analysis package. Once the model and logic are ready, they can be deployed to the controller without bringing the system offline. One more important feature in the ETAP iDLS system is the rotating schedules and planned outage management. In the iDLS system, you can build an entire year load shed schedule. The iDLS system will rotate the schedules per real time. All the operator needs to do is manually initialize the execution. The load shed execution is optimized based on the amount of load to be shed, operating condition, type of loads, and the priority schedule that is currently active. The ETAP iDLS application allows users to manually define a specific amount of load to be shed. This can be done in response to requests from the grid operator to immediately reduce the power demand on the grid. The users can select the manual execute option to first specify the amount of load that needs to be shed. After applying these settings, they can verify that the loads selected to be shed by the load sharing engine are acceptable and adequate. Upon validation of the expected response, the users can send a command to shed all the loads in one go. This is a quick and easy way to reduce the power demand on a distribution system. ETAP iDLS also provides mechanisms to create rosters where different sets of loads are shared at different times of the day. This can be done to reduce the peak demand in case of system-wide generation shortfall, disruptive weather phenomena, prevention of wildfires, or planned maintenance on the system. The rostering triggers are used to implement a feeder rotation program where certain feeders are shed for a predefined duration at a fixed time. Another set of feeders are then shed at another time while power is restored to the feeders from the previous roster. This ensures a homogeneous rotation of feeders and ensures that certain customers do not face power outage for an extended duration. In general terms, all of our ETAP iDLS controller boxes meet the same specifications. We offer rugged machines with shock protection, fanless enclosures, and support temperatures from -25 degrees Celsius to 70 degrees Celsius. In all cases, we offer remote upgrades and significant storage without compromising the size. In conclusion, the ETAP iDLS solution uses the digital twin model, real-time data, load priorities, and system disturbance to determine and shed the best combination of loads to maintain the system operating stability. It has capability of minimizing system interruptions to improve quality of service. In one integrated solution, you can validate, design, operate, and monitor a distributed load sharing system. Now let's take a look at an implementation of the ETAP iDLS solution. ETAP iDLS has been implemented and integrated with ETAP's ADMS solution at Noida Power Company Limited, NPCL, in India. The overall implementation covers NPCL's 2 transmission substations, 50 distribution substations that provide power to more than 250 feeders, and covers 100,000 customers. The system was implemented in the redundant configurations at 2 control centers of NPCL. The master control center and backup control centers are in hot-hot configuration. The MCC communicates with the substation, but if it fails, the BCC systems take over almost instantly. Originally, the load shed system at NPCL had consisted of under-frequency relays at the transmission substations. From these relays, the signal propagated to the network to shed loads. The relays were managed by the transmission companies. They had a fixed priority and were hard to reconfigure. At the time, there were less than 20 substations. Currently, the utility is growing at a fast pace, and they need an intelligent solution that can be updated from a central location and can be optimized to maintain the quality of service. The iDLS system provided a central configuration with the distributed control they needed. From the MCC or the BCC, they can configure the system. The system provides under-frequency protection. System over-demand protection is also provided. The system automatically reads the demands from the transmission network. It also provides protection to all the critical transformers in the network. There is also a provision for overload protection of the feeders. An optimized tool for rolling blackout management, NPCL uses the option to dynamically adjust priorities to minimize customer interruptions. With ETAP iDLS, NPCL has centralized the load shed management, entire distribution network visibility, prediction based on operation conditions, minimization of reliability indices impact, correlation with the transmission system requirements, and avoiding overload sharing and complete system blackout. They have saved millions of US dollars per year due to this system. Other iDLS applications include oil production fields. One nice feature for these type of systems is the capability of reducing the VFD speeds to avoid well trips. When a well is tripped, at least 4 hours and hundreds of thousands of dollars are lost in production to restart. iDLS can save millions of dollars to production fields by preventing these restarts. In summary, the ETAP iDLS solution addresses new requirements of the electrical industry. The distribution twin model provides necessary details for intelligent decisions to calculate the minimum load to shell. The system can be managed from a central location for the entire distribution network. Its predictive design provides fast response and overload sharing. It is integrated with the DERM solution to make sure quality of service is maintained. It saves millions of dollars and maintains the quality of service.